Recording.
All right, good evening, students. Welcome to Ask Mr. Rich. This is another Sunday session, and we are going to take some of your questions. If you've got any homework questions, you can post them to me in the chat here in Zoom. I will try to keep my eye on the chat to see if you have any questions. If you don't have any questions, I do have some things that I'll cover, Algebra 2 and Precalc, and I think I have some calculus things that I'll address as well. Like most Sunday nights, I do want to open up with an initial topic that might be of interest to most of my math students. And if you saw the email that I sent out earlier today, what I was going to talk about today was cell phone use. And I have a bunch of slides that I prepared on this, but it's kind of a topic that I'm pretty passionate about because as a teacher in high school, I have seen the trouble that cell phones are in the classroom and what a detriment they are to students in the classroom. And so I just want to talk to you as my students about some things you can do to ensure your success academically in terms of how you're going to use your cell phone and how you're not going to use your cell phone. So let me go through these. I'm not going to dwell on this too long, but I'll just make some comments here as we go. So there's tonight. We're going to talk about cell phone do's and don'ts for your math and academic success. And as I said, if you've got any questions for me, go ahead and post those in the Zoom chat or email them to me at askmrrich.com. All right, so about cell phones. The first thing I wanted to mention to you is it's probably no surprise to you that research has shown that cell phone usage can be positive in the classroom, that it does enhance students' research, their ability to do research. It's a lot of parents, and I would agree that it does enhance safety when there's an emergency and you need to reach out to a parent or to someone to get some help. But research also shows that they are an incredible source of classroom distraction and cheating, and just an overall detriment to student success academically and emotionally. And that's not just an opinion. There's been lots and lots of research that's been done on this. And so you probably have noticed in your school over the last several years, maybe there's been more restrictions on cell phone usage. I know in Duval County and in St. Johns County, there are pretty strict rules now that in the classrooms, you must not have your cell phone out. Only if the teacher has asked you to get it out as a part of the academic lesson. That's supposed to be the policy in the schools in this area. And now some teachers enforce that different ways. Some of your teachers may have you put it in all of your cell phones in a pocket at the front of the class, or maybe they just say, hey, keep it in your backpack. Don't ever get it out. But either way, getting a cell phone out during class is just something that's going to be an incredible distraction to you. And I know I'm not telling you anything that you don't know. And I also want to share with you that part of the research that they've done on cell phone usage in schools has led schools to realize that they have shown that schools that institute cell phone bans inside the classroom, that they have shown an improvement on their high stakes tests, kind of like their end of course exams. They've seen that if schools change their policy and are more restrictive on cell phones, they see an increase in the test performance of their students, which then is indicative of increased academic performance because of, presumably, again, less distraction in the classroom. So my do's and don'ts I tell my students is always in class, in any class, keep your cell phone in your backpack, right? Engage with the fellow students that you have around you. Always be listening to what the teacher is saying, trying to gain as much information as you can. Because as you know, and I know because I love my cell phone, but when I'm on my cell phone, I am not able to listen to what's going on around me and I will miss something. And so you don't want to miss anything in your class, especially I'm biased towards math. You don't want to miss anything in your math class. You want to hear all of this and watch all of the problems that the teacher might be working on the board. You don't want to be distracted by your cell phone where you don't hear maybe another conversation that a student's having with somebody else about how to solve a problem. There's just so much that you're going to miss out on in life when you've got that cell phone out when it's not supposed to be out. The second thing is I tell my students, minimize your cell phone usage outside of the classroom, between classes. At the last high school that I taught at, I was really surprised by how many students had their earbuds in between classes, and therefore they weren't really talking to anybody. And some of the students, they couldn't even hear me if I said hi to them as they were passing by my classroom because they had their earbuds in listening to music from their cell phone. Now, in Duval County, I know that even between classes, students are not allowed to have their cell phones out or earbuds in their ears. They have to be totally electronic device free as they're moving about on the campus. I believe that maybe they aren't as restrictive during lunch hour, but in class, movement between classes, no cell phones. Engage with people, right? Don't be on your cell phone in between classes. Keep it put away. Now, on the positive side, right, there are some things that you can put on your cell phone that can help you in your math learning. And here's three of them right here. The first one is Desmos. I have done in some of my prior Q&A sessions on Sunday nights, I've shown you some of the online resources that you can utilize. And Desmos is one of them. There's a website, desmos.com. It's got a graphing calculator, and it has an app version that is that you can put on your Apple phone, on your iPhone, or on your Google phone if you happen to have that, or your Android. And it has the same functionality as Desmos. And as you all know, I'm very passionate about Desmos because the SAT College Board platform that they use on the test, their calculator is Desmos. So the more that you can learn the capabilities of Desmos, then the better off you're going to be when it comes time to utilizing it on the SAT. So Desmos is something that you want to have on your phone. So if you're at home and you're studying and you need to graph something, yeah, you can use your phone to do it. Another one, I did talk about another website called Wolfram Alpha. It's a strange name, but there is an app for Wolfram Alpha. And that is, I call it kind of the Google of solving math problems, and where you can type in an equation to be solved. You can ask it to do something mathematically, and Wolfram Alpha will do it. And it'll even show you the steps to it. So if you're working a problem and you feel like you need somebody to coach you and show you the steps, Wolfram Alpha is an excellent tool to have on your cell phone. Now, well, that's it. I think there is a charge. There may be a charge still on Wolfram Alpha to load it onto your device. I loaded it several years ago, $6 or $7, and it gives you the full functionality of Wolfram Alpha. So, and I think it's definitely worth it. If your teacher happens to use Delta Math in class, then definitely you want to bookmark Delta Math in your browser on your phone, because you can work problems in Delta Math on your phone. So those are three, and maybe you have some others. If you do, put them in the chat. I'd like to know about it and take a look at them. So you can load apps. Another thing that I would recommend that you could use your cell phone for on a positive side is in your class, set up a text group with your fellow students or a study group where if you're working on homework at home and you need help and you need to talk to each other, sure, you could text each other help on the homework. Or if someone solved a problem that you weren't able to do, they could send you a picture of what they did and you could check your work against theirs. So just one other way that you can do that to communicate with the students that you're working with. But finally, I guess the last thing I would say is that it's not just students, right, that need to not let cell phones be a distraction. I always was telling my students, it's all of us. It's all the adults, all the students. If we are not careful, our cell phones can be a detriment, not just to our education, but to our personal lives and in our personal relationships with our friends and family members. So we have to really be cognizant all the time of, hey, should I really have my cell phone out right now? I have to I find myself maybe reaching for my cell phone to check my email when I'm around my loved ones. I don't want to do that. I want to minimize that as much as possible. So anyways, that's my spiel on cell phones, do's and don'ts. I hope it was helpful. All right, what I'm going to do is let's stop this share here. And I'm going to take a look and see if we have anything in chat. It doesn't look like it. And we will get right to it. And here we go. I'm going to do some Algebra 2. How about that? I am sharing my screen. I hope that you all can see this. I'm going to work some problems in Algebra 2 that if you are an Algebra 2 student, you may have gotten to this unit by now. And what I'm going to do first is solve some problems here where it's asking us to give the coordinates and classify the extrema for the graph of each function. So I'm going to take a look at this quadratic function, number 11. There it is. It is a quadratic, 2x squared plus 4x minus 5. And as you probably know, quadratics make parabolas when you graph them in the xy plane. And parabolas, one of their characteristics is they will have a minimum or maximum value. And that's what we call an extreme value. That would be what we call a relative minimum because it is a valley. And the coordinates of that point happen to be -1, -7. All right, let me show you one that's a little bit more complicated. This is a polynomial. This is what we call a fourth degree polynomial, x to the fourth minus 4x cubed plus 9x. What I'm looking for on extreme values is I'm looking for those peaks and those valleys that occur in the function. And I notice there's 3 of them. I have one here, here, and here. So what I have is I've got 2 relative minimums. We call these relative minimums because they aren't necessarily going to be the absolute lowest value. They're the lowest value in the vicinity of where the point is. Now, this does happen to be the absolute lowest point on the graph, but because it's a valley, we call it a relative min. And here's how I would classify this, right? This is a relative min. It does occur, it looks like it occurs not quite at -1 and not quite down here at -5. So I'll say that there's a relative minimum at x equals, it's approximately -0.8. And the value is approximately 1, 2, 3, 4, maybe y equals a -4.8. So the actual value at that point is -4.8, and it occurs at the x value of -0.8. Then there's another relative minimum over here. It looks like that might be at a relative minimum at x equals maybe 2.7, and its value, its y value, looks to be, oh, maybe a -1.2. And then there's a relative maximum. I have a peak up here. So I could say that this function has a relative max that occurs at about, I'll call it at x equals 1. It looks like it's a little bit beyond x equals 1. And it looks like it maxes out at about 6. 1, 2, 3, 4, 5. That has a y value of 6. All right, so those are what we call relative extremes. Now, one of the other things that you're going to have to do with graphs is in Algebra 2 is you're going to have to give intervals on which the function increases or decreases. And I'm going to explain how it is that we're going to do that. So I'm going to pick this quadratic first. So it's asking us to give intervals where it's increasing and intervals where it's decreasing. Now, what does interval mean? When it's asking you for intervals where it's increasing or decreasing, it's implying that you're supposed to give it x values. In other words, give me all the x values for this function where it is decreasing. Well, when I look at this parabola, I know that this section right here is a decreasing section because if I was walking on top of the function, moving left to right, I would be descending down the curve. And so it's a decreasing area. If you want to think of it another way, if you drew a little line segment to represent that portion of the graph, it would have a negative slope. So therefore it's decreasing. Now, where does it stop decreasing? It stops right here at the vertex of the parabola, which is also the location of a relative minimum. So what I know is that this function goes forever up and to the left. So the x values for which it is decreasing is going to be from -infinity up to -2. And that looks like an ordered pair, but it's not. When we give intervals in Algebra 2, we are giving the lowest value and the highest value, the lowest x value and the highest x value for that interval. So it's decreasing from -infinity to -2. Notice I'm not putting a bracket here because that wouldn't indicate that I'm including -2 in this interval. And I don't mean to do that because when I get to -2, it's no longer decreasing, nor is it increasing. It's kind of flattened out at the very bottom of this valley. So I'm going to indicate that by a soft parentheses. It's going to pick up increasing on the other side of -2 all the way to infinity. And that's where the function is going to be increasing from x equals -2 all the way to x going to infinity out to the right. Okay, let me check to make sure, see if there are any questions coming in. Doesn't look like it. Let me go check one thing here on my chat. All right, let's go back and share my screen. Here we go. Let's do one more. So these are absolute value functions. Most of you in Algebra 2 have been working with absolute value functions. That's what this is. If I had to give an interval over which this function is increasing, it's going to be this section right here because the slopes are positive, or picturing it, if I was moving on top of this function from left to right, I would be on the ascension here. And then over here, I would be on the descension. So that's where it's decreasing. Now, since it goes forever in this direction, the increasing interval is from -infinity up to this very top value, which looks like it's going to be at about an x value of 2.5. Okay, I'm not reading y values here, right? I'm not saying, well, it's going up until it reaches. No, I'm not worried about on my intervals the y coordinates, just the x coordinates. Then the function begins to decrease when it gets past x equals 2.5. So it would be decreasing on the interval from x equals 2.5 all the way out as x moves towards infinity all the way out to the right-hand side. And I want to do one more, and then we'll move on to maybe some pre-calculus. What I'm going to do on this one is I'm going to do two things. I'm going to give intervals over which it's increasing, and then I'm going to give intervals over which it's positive or negative. So it's going to be increasing on this branch right here. And this goes all the way down and to the left. So the first increasing interval is from -infinity until this x value. And you know what? Just for simplicity, I'm going to call that a -2 on the x-axis. But after it gets past -2, it's decreasing, but then it looks like it's going to start increasing again down here once it gets past this valley. So the next increasing interval would start, let's call that 0.5, and then it would go all the way out to infinity because it's going to be going forever up and to the right. The only decreasing interval would be this one between this relative maximum and this relative minimum. So the decreasing interval would be from -2 over to 0.5 on the x-axis. That's where it's increasing and decreasing. The other thing that your teacher is going to want you to find on these functions is where are the intervals where the function's positive or negative. So I could say, give me the intervals such that f of x, the y values, are greater than 0. Well, when is a function positive or greater than 0? It's going to be when it's above the x-axis. So this little piece right here would be one place where the function is positive. The other one is going to be over here once it gets past that x-intercept right there. So the first interval where the function is positive would be read off the x-axis right here. It looks like it's, let's call it at -2.5. And then it stays positive until it crosses the x-axis here at -1. Then when it gets beyond 1.5 all the way out to infinity, and the function is again above the x-axis, and we would call it to be positive at that point. Where is the function negative? When is my f of x going to be less than 0 or negative? Well, that's going to be where it's below the x-axis. And it's below the x-axis to the left of this x-intercept here at negative 2.5. And this leg here, this part of the graph goes forever down and to the left. I know it looks like it's almost vertical, but it's not, right? It keeps going down and to the left. So that means it goes all the way along the x-axis to negative infinity. It's going to be negative until it gets from negative infinity to negative 2.5. And then it will be negative once again, once it gets past negative 1, and then comes over here to an x value of 1.5. So those are my two intervals for negative. Those are my two intervals for positive. And that's the kind of thing that you're starting to do in the next unit of Algebra 2. Let's move on to Precalc. Now, most of you are about in lesson 1.7 for pre-calculus. And I'm just going to jump to working a few of these problems. If you were paying attention to Algebra 2 towards the, I believe it was in the third quarter, maybe fourth quarter last year, you pretty much know everything in 1.7 of AP Precalc. And what they're dealing with in 1.7 and 1.8 and 1.9 are going to be what we call rational functions. Rational functions are functions that are ratios of polynomials. Like this right here, I have a linear or first degree polynomial on the top. I got a second degree polynomial on the bottom. And actually, I'm going to start with 1.7a. I'm going to go down here to this. So let's take a look at this rational function. So there's our rational function. The very first thing that they're teaching you in 1.7a is how do we determine the domain of rational functions? Domain is the allowable x values that are part of the function. Well, it's very simple. It's all real numbers except any of the x values that would make the denominator equal to 0. So when I'm trying to find the domain of a rational function, I'm going to start with the premise that it's all real numbers except for the ones that would make this equation, x squared minus 16 equals 0, the ones that would make that true. Because any value of x that I would stick into this function to evaluate it that results in a 0 in the denominator makes the function undefined. Because one thing you know about division, we can't divide by 0. So anyways, there are two solutions to this equation. Two methods of solving this would be to add 16 on both sides and then square root both sides. And when you square root 16, you get two answers. You get a positive 4 and you get a negative 4. The other way to solve it would be to factor using the difference of two squares, which is one of the special factoring methods that you learned back in Algebra 2. So the other pathway to solving this would be to say, well, this thing factors into x plus 4 times x minus 4, and therefore I can set each of those two factors equal to 0 and solve them, and I get my two answers, x equals negative 4 and 4. Now, those are the two exclusions to the domain of the function. Plug in any value of x and you'll get a y value except for those two x values. One of the things that you've been learning in AP Precalc is the idea that we use interval notation. And I was just showing you some interval notation in the Algebra 2 problems. And sometimes teachers don't use interval notation. Sometimes they use what's called set builder notation. So some of you may be writing them in that form. But when we get to AP Precalc and then into AP Calculus, not really using set builder notation to indicate intervals. Instead, what we're going to do is say, and I'm going to write it out this way just to make an explanation as to how the interval notation works. If we take a look at all the possible x values, there's only two that we have to skip over, negative 4 and 4. So that means if I was to like visually display the domain, I would put a hole or a circle here and say it's all the numbers to the right of 4, it's all the numbers in between 4 and negative 4, and then it's all the numbers to the left of negative 4. What I'm going to do is I'm going to write an interval, a low and a high, for each of those three regions that I just created, 1, 2, 3. Well, this interval would be from negative infinity, because this thing's going all the way out towards negative infinity, from negative infinity up to, but excluding negative 4, unioned with the next one, which starts at but excludes -4 goes to 4, unioned with 4 to infinity. That would be the domain for this particular rational function expressed in interval notation. All right. Let's see if we got any questions here. No. So remember, if you've got any questions, feel free, type them in chat. Anything that is not clear or you want me to go over, or if I make a mistake, then be sure to let me know. Let's share the screen back. All right, let's do another domain. Here's a rational function. I have a polynomial on the top. I got a polynomial on the bottom. The domain for this function is going to be all the values of x except any that might make that equal to 0. So I'm going to set that denominator equal to 0 so that I could solve it and know what the exclusions are to the domain. First thing I'm going to do to solve this is I'm going to factor out the greatest common factor of 2. That will make my factoring much easier. So that's going to give me this, right? And it's a quadratic, and I'm going to solve this by factoring, and this can be factored. This is going to be x and x, and then I'm asking myself what two numbers would multiply to give me a -14. So one of them's got to be positive and one of them has to be negative, but I also want them to add up to be the middle term coefficient of +5. That is a +7 and a -2. Then what I do to get my solutions to this equation is I set each of the factors equal to 0. And when I do that, I get x equals -7 and I get x equals 2. So those are the two exclusions to the domain. Those are the two values that if I try to do h of -7, it'll give me a 0 in the denominator, and I don't have an answer for that because it doesn't exist. I can't divide by 0. So therefore, I will express my domain as going from -infinity to the next number, -7, but I'm going to skip over -7. So I'm going to go from -7 to 2, and then from 2 to infinity. This is what excludes those two values, right? -7, and then the 2 right here gets jumped over because, as I said, in interval notation, and in case you missed it, I'm going to show you. Let's take a look at this interval here. This says x is greater than -2 and x is less than 4. If I were to write that interval from -2 to 4 in interval notation, it would look like this. And the parentheses next to the -2 and the 4 indicate that I'm not including those two numbers in the interval, because this -2 is not a solution to this because x must be greater than -2. But if I write it like this, suppose that I changed this to be x greater than or equal to -2 and x less than 4. I still would put -2 and 4 as the boundaries of my interval, but this one's going to get a bracket and that one gets a parentheses. This tells me that it's from -2 and including -2 up to 4, but excluding 4. That's interval notation. The other thing that we're going to cover in 1.7 is the idea of what we call horizontal asymptotes. So when you look at this function back in Algebra 2, right, this was an Algebra 2 problem in about the third quarter. You're given a rational function and you have to determine, are there any horizontal asymptotes? And what we taught you in Algebra 2 was that if you look at a rational function and the highest degree on the top, in this case, x to the second, it's a second degree polynomial on the top, and you have the same degree on the bottom, x to the second, you do have a horizontal asymptote. And that horizontal asymptote is going to be located on the horizontal line, y equals the ratio of their two coefficients. So in other words, this coefficient is a 1. That one is obviously a 1. 1 over 1 is 1. So if I were to graph this, I would see a horizontal asymptote at y equals 1. What they're going to show you to do, your teacher will probably have you do this in class if they haven't already, is they would have you pull the TI-84 out and actually have you put the function into your equation editor of your TI-84. And then what they want you to do is fill out this table. So I've got the equation already entered in there. And what I'm going to do is I'm going to tell my calculator to create a table of values of X and Y's. So I'm going to do second function table set. And I'm going to tell my calculator to ask me for the X values. This word independent does stand for the X values of our function. The dependent is standing for the Y values. So I am selecting the word ask because I want to put in my own X values. What X values do I want to put in? I want to put in these, negative 10,000, 1,000, and so on. And so I'm going to tell it to ask. I'm leaving the depend on auto because I want it to automatically calculate the Y value when I give it the X value. I'm now going to click on second function table. All right, now this is left over from what I was working on earlier, but I'm going to go ahead and put in negative 10,000 into the table. And it calculates, it sends that negative 10,000 back to the equation that I saved in Y1. And you can see the header here says Y1. It tells me that the answer, when you plug in 10,000 to this function right here, a negative 10,000, the answer is 2,500 over 2,501. If I tell it to put in negative 1,000, you can see I already did that. It gave me 250 over 251. What is this telling us? Well, hopefully you realize that 2,500 divided by 2,501 is almost one. It's very close to one. It's 0.999. Okay, it's just under the number one. This tells me that the further left I go, look where I'm at. I'm way out to the left on my x-axis at negative 10,000 units. And the y value is very close to 1. That means this proves to me that there is a horizontal asymptote at y equals 1. Is there a horizontal asymptote? Yes. And where would it be? It would be at the equation y equals 1. Because the further left I go, the closer my y values get to the number 1. On this table, notice over on the right side of the table, it wanted me to plug in a positive 10,000. Well, I think I did that. Positive 10,000 gives me 2,500 over 2,499. 2,499, like that. So that tells me as you go way out to the right on the graph, the function is going to get very, very close to the number y equals 1. Now, what it does tell me, though, it does give me a little bit of information about like where it's coming from. In other words, if I were to take a look at this graph at y equals 1, there is a horizontal asymptote indicated by that dashed line. But for the fact that this number is slightly larger than 1, right? 2,500 is bigger than 2,499. So it's slightly bigger than 1. It tells me that this function is coming into the asymptote from the top as it goes out to the right. This one tells me, since it's slightly lower than 1, that the function's coming into the asymptote just underneath 1. So it's going to behave something like that out on the extremes. I haven't at all determined what's going on in between, like towards closer to the y-axis. The only thing we're considering is what we call the end behaviors out on the extreme fringes of the x-axis. So you have learned in 1.6 how to express the end behavior of a function. If I know that there's a horizontal asymptote at y equals 1, the way that we express this is we say that the limit, LIM stands for limit, the limit of our function's y values as x goes to infinity is equal to 1. That tells me there is a horizontal asymptote at that value of y equals 1. I also know that this table is telling me that as I go out to the left, as x goes way out to negative infinity, it's also approaching 1. So there's nothing really new here in horizontal asymptotes except the way that we are expressing in AP Precalc the end behavior. We're using these limit statements. So you'll explore that a little bit more in 1.7 and even into 1.8. All right, I'm going to move on now to calculus. I do have some AP Calculus AB students, and we are going to solve this kind of as our last problem tonight. This says to find the equation of the tangent line of f of x at the given x value. What you learned in the last couple weeks in AP Calc was you learned the definition of a derivative of a function. In other words, we learned that f prime of a, which is the derivative of function f, is expressed by this limit. The limit as h goes to 0 of f of a plus h minus f of a all over h. If you're not an AP Calc student, right, this looks like Greek, right? What in the world is this? What is even f prime of a? What are we talking about? Well, in calculus, when we have a function, in this case, f of x equals the square root of x, there is another function that's related to it called its derivative, which is called f prime of x. And that derivative function gives us the slopes of the tangent lines to this curve for any of the x values in its domain, provided it's differentiable at those points. And so this is what we're going to do. So if I'm going to find, they want me to find the derivative, or excuse me, the equation of the tangent line of f of x at x equals 9. So my first order of business is to find f prime at 9. And I'm going to use this limit definition. So I'm going to say it's the limit as h goes to 0 of f of 9 plus h, right? Because my a value is a 9. So it's going to be f of 9 plus h minus f of 9 all over h. Now I'm going to proceed to evaluate this limit. Well, f of 9 plus h. Well, if you know anything about limit notation, you know what that means. That means you're going to go stick 9 plus h in place of any of the x's. So this would be the square root of 9 plus h, like that, minus f of 9, right? This was, look, my a's and 9s are hard to differentiate between. That's supposed to be f of 9. Well, f of 9 means go stick 9 in for x into the function. That would be a 3. Square root of 9 is going to be 3 minus 3 all over. Those of you that are familiar with evaluating limits, you know that if I tried to substitute 0 in for h, I would get 0 over 0 at this point, because this would be the square root of 9, which is 3, minus 3 all over 0, because I'd be sticking the 0 into this h. And you know that 0 over 0 is what we call indeterminate. It means we don't know what the value is going to be for that limit. It means we have more work to do in terms of simplification. Now, one of the things that you learned in your limits unit was how to simplify this when you have a binomial with a radical. And what we're going to do is we're going to multiply the top and bottom by the conjugate, root 9 plus h plus 3 on the top. But if I do that on the top, I also must multiply the bottom by the same conjugate, square root of 9 plus h plus 3. And most students, when they see that, they're like, how was I supposed to know that's what I was supposed to do? Well, you weren't really, until we told you that if you have a radical binomial with an indeterminate form, when you stick the 0 in for h, yeah, try multiplying the top and bottom by the conjugate. Because here's what happens. When you multiply two conjugates, two binomial conjugates together, the outer and inner products are going to cancel. And all you're going to be left with is the product of the first two terms minus the product of the last two terms. When I take root 9 plus h times root 9 plus h, it leaves me with 9 plus h. When I multiply negative 3 times positive 3, it gives me a negative 9, like this. And then down in the bottom, I have h times the root 9 plus h plus 3. Now, at this point, you're like, okay, where is this going? What is going to happen here? Well, what happens is I can now simplify the numerator, because this numerator now is just going to be h, because 9 minus 9 combines to 0. I have h over h times root 9 plus h plus 3. Now is where the magic happens. Now what I have is I've got the simplification of getting rid of the two h's. common factors, top and bottom, they cancel. So now I'm putting this in all of its gory detail here. This is the limit as h goes to 0 of 1 over the square root of 9 plus h plus 3. Finally, at this point, I'm ready to use what we call direct substitution. I'm ready to plug in 0 for h and then evaluate the limit. I can do it because I will no longer get 0 over 0 when I plug the 0 in for h. When I plug the 0 in for h, I can get rid of the limit and I get 1 over the square root of 9 plus 3, which is 1/6. So what that tells me, all of this work, it tells me that the derivative of my original function evaluated at x equals 9 is 1/6. Okay, we're still not done because the original question was asking us to find the equation of the tangent line of this function f of x at x equals 9. So now I'm ready to make the equation of the tangent line. Here's what we always start with in calculus when it comes to writing an equation of a line. We're going to use what we called the point slope form of a linear equation. This is something that you learned back in Algebra 1. If you're trying to write an equation of a line and you know the slope of the line and any of the points that you know fall on the line, that would be the x1, y1. Pick any point on the line, throw it into that point slope form, put the slope in for m, and you've got your equation. Well, this 1/6 right there, that is the slope of the tangent line, because that's what derivative functions are. It's the slope of the tangent line at x equals 9, 1/6. So, and I'll show this to you graphically here in Desmos in just a second. But that tells me then that when I'm building this equation, it's going to be y minus y1 equals 1/6 times x minus x1. Well, what point do I know is on the line? The point that I know that's on the line is the point up here, f of 9, right? What is this function? In fact, we evaluated f of 9 as a part of this whole process, but f of 9 is 3. Square root of 9 is 3. So in other words, one of the points that's going to be on this tangent line is 9, 3. In fact, it's the only one that I know that's going to be on this tangent line, because that's where the tangent line is going to hit this curve y equals f of x. So now I'm just about done. I've got it. I know that this is going to be y minus 3 is equal to 1/6 times x minus 9. That right there is the equation of the tangent line that will hit the curve y equals f of x at x equals 9. I will modify this slightly. I'm going to move the minus 3 to the other side, and it'll become a positive 3 over there. And that's going to be my equation. So what am I going to do? I'm going to go now and show you what all this means from a graphical perspective. So let's go to Desmos. First thing I'm going to graph is the original function, y equals f of x. Y equals, I should say, square root x, rather. There's the function. I'm going to rescale this slightly so we get a little bit better look at it. On the y-axis, I really only want to look at values from, let's say, from -1 up to about 4. Let's go to about 7. How about 9? There we go. That's good. So there is the function y equals the square root of x. I'm going to go ahead and graph this linear equation right here. And let's hope it works, right? Y equals 1/6 times x minus 9 plus 3. Okay, that's interesting. I'm going to rescale this on the x-axis, yeah, because we're looking at a little bit too wide here. We'll go from -1 to 6. Yeah, 12. How about that? Okay, there we go. What is happening is that if you come out here to where x is equal to 9 and you come up here, that right there, that point, 9, 3, that's where this green line comes along and nicks the curve square root of x at that point 9, 3. That is the tangent line. That represents the slope of that line, which we know is 1/6. It's the rate of change of our function, square root of x, The 1/6 is the rate of change of the function at exactly that one point. And so that's the equation of the tangent line right there. And we did that with the limit definition of a derivative. And one thing that you'll learn as you go through probably the next 4 weeks, you're going to be learning the rules of derivatives, and you're going to realize finding the derivative using rules of derivatives takes you, maybe 15 seconds versus maybe 10 minutes using this limit definition. So this, though, is kind of the whole beginnings of calculus, understanding limits, and our understanding of derivatives comes from this limit definition of a derivative. So that's why we teach it to you. But now, as we move beyond limits, and you'll be learning the rules of derivatives, that's how you're going to be taking derivatives moving forward. All right, class, that is going to be it, I think, for tonight, unless I see any questions. I don't see any questions. Let me make sure that there's no questions that came through by email. Did. Anyways, I wish you all a great week ahead, and I hope to see some of you again next week. We'll be doing